away.
I just started it.
That's okay. Hello there, Brandon, Hunter. This is Tuesday, and we are reviewing from yesterday. So we started Mod 5. We're in a notebook with a new divider, and we had day 1 notes going yesterday. And without too much reliance on them, what was the other name for Newton's first law, Emily?
The law of inertia.
The law of inertia, very good. All right, what is the unit for force? Zach?
With Newton in the
Metric.
in metric.
Right, okay, we'll let someone else tell us the unit for force in America. We call it English. So, what's the English unit? Do you recall, Emily, number 3? When you stand on the scale.
Oh, pound.
A pound, right, alright, very good. Alright, so before we named it the Newton, before we named it the pound, it was just a combination of units. Does anyone recall that special combination of units that make a Newton? I'll give you one if you give me the other 2.
I probably know the one that she.
What was it? Do you recall, Alex? We're talking about the Newton.
Newton.
It was something divided by something, and I'll give you kilogram.
Oh wait.
What are the other 2 parts for the Newton?
Thanks, Emma.
Kilograms times acceleration times meters per second squared.
Right, very good. All right, so we renamed that the Newton, and what did pound used to be? Emily, number 1, or it still is, but we renamed it something divided by something.
Slug.
Slug.
Feet.
Right. Slug
second.
feet per.
Zoom in.
Second square.
All right. So a slug foot per second squared is a pound. So try that one on the nurse that weighs you at your doctor's.
I'm going to take my slug.
I need my slug. Weight and slug.
My slug foot per second.
No, I'm going to go in and say, can I be weighed in newtons? I said, I prefer to be weighed in newtons.
I think they probably
All right.
just do conversion.
All right. So is there any
I
other?
think they would just look at
oh,
you
I
and say
know.
no.
Brian, is force a vector quantity or a scalar quantity? It is a vector quantity. All right. I think those are some of the major parts. So the fundamental equation in physics is, I guess that should be reviewed because it's fundamental. Emily, number 2.
The sigma of F equals ma.
Right, the sum of the forces equals ma. And that's where we left off with the man pushing a rock, and we were just using that formula, plugging in what we knew of the 2 and finding the one that was left out. So that led us to our OYOs. So let's see. Maybe you pull out your work and I'll check you off for that. We did 1, 2, 3, and 4. So, and we'll go over them. I'm not going to collect them, but I will check them off as being done. So let me peeky poo at them. All right. Where's yours? Oh, over here. Emily, number 1, 2, 3.
I left my book at school.
Oh, Zach. All
Well,
right.
my binder.
Brian.
Not the book.
That happens to me so many
I'm
times.
sorry.
I don't know.
Oh, yes, 1, 2, 3, and 4.
I will show it to my literature class without the book. With the binder, but without the
Did you
book.
get the
Kind of
assignment?
important.
Yeah, neither did I.
All right. Well, it was announced. So,
I'm gonna work faster than you.
okay, see. All right, and Hunter, Brandon are. All right, we're gonna go over them now. So on number 1, it said you started your Christmas shopping early and are driving on a highway with several packages. Suddenly you're forced to accelerate quickly in order to avoid hitting a car getting on the highway. You notice that even though the mode is level, the packages slide backwards. Why? All right, could you explain it to us, Emily, number 1?
Because there was friction between the packages and the seat.
I'm sorry?
Because there was friction between the packages and the seat.
All right, but what there is friction there, but it doesn't really explain why they went backwards. If there was enough friction there, it would have stayed. Yes.
I put that because of the law of inertia saying that an object wants to stay where it was initially.
Right.
So it will want to be towards rest, I guess.
It wants to be
like
towards
where
rest.
it was. I was having trouble phrasing it, but like it wants to be where it was initially, and so if you're going forward, it wants to pull back.
All right. Yeah, all right. You're getting close. I think you are there. It's just that the wording is a little. Emily. All right, Zach, you up to that one? Number
Yeah.
3? Number 1.
Is it because it's the Newton's first law is an object in rest will stay in rest, and object in motion will stay in motion unless acted upon by an outside unbalanced force. And
Right.
so the unbalanced force.
force.
So the unbalanced force, when you someone brakes, is going to push it forward, even though it wants to stay in rest. It's acting.
So, but the package is going backwards.
You're excited.
It's accelerating. Emily, 3.
You still want me to do these problems
Pardon?
You still want me to do these problems tonight?
Are we filming the problems?
Oh, do you want me to still do the problems tonight?
Oh, yes.
The packages want to stay at this original speed that they were at, so that when somebody speed up, they're still going the same speed.
Right. All right, she got it. So that like her wording. So the package is going the same speed as the car, and when the car speeds up, the package says, you know, I'm going this speed. I'm not going any faster, so it'll slide backwards. So keep that in mind when you're transporting your hot dogs to the bonfire tonight. All right, on number 2, we all know that if you slide a block on wood on ice, it will travel much further than it does on concrete. Use the law of inertia and the concept of friction to explain this fact. So, let's see, back to you, Emily, number 1. So, inertia says what and why does the block stop? But it goes further. Put all that together.
So the Newton's first law is an object in rest will stay at rest, and an object in motion will stay in motion unless acted upon by an outside force. And so the different surfaces have different levels of friction, and so the ice has less, so it'll keep going more. than
Right,
the
so
concrete.
the ice has reduced the friction. It would go forever according to the law, but friction will stop it. But since there's little friction, as we've all experienced, it'll keep going for a long time. Anyone have an ice story? Have you ever been on real ice, like pure ice, and just have no ability to stand? It's a really, I remember I went to the car and it was ice under, and I lifted the handle. Guess what happens when you have no friction? You lift the handle.
You lose your balance.
You fall back. So next thing I know, my back of my head is on the ice. So,
Ouch.
and as quick as that, and my feet are under the car. It's like, how did this happen? So, friction, very important. It's our friend, it's our enemy. That day it would have been my friend. Number 3, a man is pushing a car. So we had to work out a problem on number 3. He pushes with a force of 15 newtons, and the car has a mass that's given. What will the acceleration be? Have you got that far, Zach?
Yep, just now, but.
So, it's not a rock, it's a car. Alright. Alright, a man pushes the car because he's run out of gas, 15 newtons, west, and the car has a mass of 1.23 times 10 to the 6 grams. What will be the car's acceleration? You want to talk us through that one, Zach?
Okay, so you move it over 6 decimals.
Alright.
So you get
1, 2, 3, 4, 5, 6. So that's grams.
mhm.
So now what?
And then
What is the force? What is the mass? What is the acceleration?
the force is 15.
Right, newtons, remember newtons is force, so we put in a 15. But once you put that 15 in, you're working in
So
kilograms.
you make it 1,230 Oh, yeah, just.
Yeah,
wait,
one
never mind,
thing.
Pardon?
No, he's right here, 'cause it's 3.
Wait, no.
100.
But the
No, it's
original number, you need
1,230.
extra zero.
What's that? Oh, yeah, 1, 2, 1, 2, 3, 4, 5. I forgot a 0. Sorry, Zach. I
No,
led
you're
you.
fine.
I led you astray. So,
It's so true.
1,230, you're right, is the mass in kilograms. And can you get
And
that
that is-
calculation for us?
Meters per second. Okay,
So how much is it? Tippy tap that out.
it is 0.01219.
0.0129.
19.
0.019. Okay.
No, 1219.
Oh, okay. So now, how many of those can we accept?
We can only accept 3.
Did you say 15?
Oh, 2, because
I
of
didn't-
15.
Is it? I don't know. Did you
And
look how
I
it was
looked
written?
in the back or wherever it was, and
15.
it had 3.
Oh.
15. It should be 0.012.
That's what yeah.
See, that's not significant.
Yeah.
So 0.012. So that's 2 sig figs. And what unit?
Meters per second. Squared.
Right. All right. So that's the acceleration coming from the force formula. They'll give us 2, and you have to solve for 1. All right. All right. Last one. Another theory one. A tennis ball bounces. How can you tell that a force other than gravity must have acted on it, Emily?
Me?
That's right.
Okay, well, you can tell it because it changed direction.
Right. Because remember, I said yesterday, anytime there's an acceleration, which is a change in velocity, there must be a force applied. So when something changes direction, remember velocity is a vector. So if it changes direction, there has been a change in velocity, thus an acceleration. They're all linked together. All right, at what point did the force act on the ball also, Emily? Number 3. What point did that happen?
When the ball hit the ground.
All right, here's an.
It's really scary.
Alright, where did it change directions? Obvious, right there, when it hit the table. Alright, and what is the general direction of that force? So there was a force acting on the ball to change its direction. What is the, Emily number 1, what's the direction of the force that the table's exerting?
Up.
Right, because it was going down. And now it's going up. The table pushed it upward. And what's the general direction of the acceleration? Emily number 2.
Up.
All right, because whatever these two are doing, they match because they're equal. So if force is going up, so is acceleration. All right.
All right, can I stop this?
Yeah, is it how many minutes?
It's like 13, but I stopped.
Yeah, that's perfect. All right, that's a good stop.